Alright guys, for day 2, for section 3.1 additional problems, we're going to, be needing a graphing utility calculator. So if you do not have one handy, please get one out. Because we're going to be determining the vertex using what we know about quadratics and our functions. And then we're going to be determining if each chord has an x-intercept or not. Note, I did not say find the x-intercept. I said, does it have an x-intercept or not? This is simply yes, no, and how many. Okay, so 12a, we have x minus 2 squared minus 5. Well, if you know anything about our vertex form, like we've been going over, we know that this is going to have a vertex of 2, negative 5. All right, so now we need to know, okay, 2, negative 5, somewhere down here, and it points up. So we know that it's going to cross and have 2 x-intercepts. But, of course, it says use a graphing utility to verify, so I'm going to go to y equals. I'm going to do my parentheses, x minus 2, close my parentheses, squared, minus 5, and we're going to hit graph, and we're going to take a look at it. There it is. We have 2 x-intercepts. All right, b. b is given us as a quadratic formula, so we're going to have to use our formula for finding the vertex. So we know that we're going to have to use negative b over 2a, and then we're going to have to take and plug that answer in to find our vertex. So we have a is 1, b is 4. I'm not worried about c. So I'm going to say that is a negative 4 for 2 times 1. Oh, that's negative 4 over 2. Negative 4 over 2 is going to be an answer of negative 2. So we're going to use our calculator, or not use our calculator, sorry, we're going to plug it back in using our parentheses. So negative 2 squared plus 4 times negative 2 plus 4. Negative 2 squared is a positive 4. Positive 4 negative 2 makes that a negative 8. Plus 4, well, 4 minus 8 plus 4 all cancels each other out, so we get an answer of 0. So we have a vertex at negative 2, 0. Lead coefficient is positive. It starts at a negative 2, 0, but we're going to double check and take a look at it. Again, I'm going to clear that out. I'm going to go x squared plus 4x plus 4. And I'm going to take a look. Negative 2, 0. Oh, notice about this one, negative 2, 0. It actually touches the x-axis at the vertex and nowhere else. So it only has one x-intercept, and it happens to be negative 2, 0. All right, now we have 2x squared plus 6x plus 7. Again, this is not vertex form, so I'm going to have to use my formula. I know a is 2, b is 6. Plug it in. Negative b over 2a is negative 6 over 4. If I reduce negative 6 over 4, I should get a negative 3 halves. Some of you forgot to do this on your homework or your assignment 9. So please remember, always reduce. So we get a negative 3 halves for our x, and we're going to have to take 2 negative 3 halves squared plus 6 times negative 3 halves plus 7. I could make you do this by hand, but what I'm going to do is I'm going to hit second quit, and I'm going to take, and I'm going to say 2 times negative 3 over 2 squared plus 6, again my parentheses, negative 3 over 2, close my parentheses, plus 7. I'm going to verify and make sure that I put everything in exactly the way I needed to, using negatives and not minuses, and closing all my parentheses where I need to. I'm going to hit enter. I get a decimal, 2.5. Well, I don't necessarily deal with decimals, so I'm going to hit math, and I'm going to hit enter because I'm going to change that decimal into a fraction to get 5 over 2. So I have negative 3 halves and 5 over 2. If you give the first part in a fraction, then you need to give the second part in a fraction as well, but you can also give this in a decimal form if you need to give it into a decimal form. So what we do know is that this is a negative x and a positive y, so I know it's going to be in the second quadrant. It's facing up. So it's in the second quadrant, somewhere here, and it's facing up. It never crosses the x-axis. And if we remember from our homework that we did the other day, we have 2x squared plus 6x plus 7, which I think was probably this point. If it never crosses the x-axis, then it has no x-intercepts, in that it has no physical x-intercepts. It has irrational ones, but we're not dealing with those right now, so we're going to say that it has no x-intercepts. So this is my answer here. For D, x squared plus 3x minus 8. Again, a is 1, b is 3. Negative b for 2a. Negative 3 halves. You can either say negative 3 halves or you can put it in decimal form. I just leave everything the way it is because I know my calculator can take care of that for me. So negative 3 halves squared plus 3, negative 3 halves minus 8. Again, I go into my calculator. I don't want the y equals, so I'm going to hit second quit, clear out. And again, I'm going to put it in exactly the way I have it written. Negative 3 halves squared plus 3 times negative 3 halves minus 8. Enter. I get a decimal, negative 10.25. Now, again, if I'm giving x as a fraction, then I need to give my y as a fraction. So I'm going to hit math, and I'm going to hit enter, enter, because I want it to be a fraction, so that I get negative 41 over 4. So negative 3 halves, negative 41 over 4. Again, you could also give this as negative 1.5 and negative 10.25. Both of these are correct answers, okay? But if you're giving one as a fraction, you have to give the other as a fraction. If you're giving one as a decimal, the other one has to be a decimal. Okay, we like consistency in our mathematics. So we're going to take it and we're going to plug it into y equals so that we can see what it looks like. First of all, we notice it's positive, and it's going to be in the negatives, so more than likely it's going to cross the axis 2 points. So, but we're going to double check it. X squared plus 3x minus 8. Again, I'm going to hit graph. I'm going to take a look at it. Obviously, it actually crosses and has 2 x-intercepts. So either one of these is correct and 2 x-intercepts. All right, E, x squared minus 16. Well, how am I going to do negative b over 2a if there's not a b there? Well, it's an understood b, so I have x squared. Technically, this is like a 0 is there, but he's not because he's a 0. But he's an understood one, so we know that a is 1 and b is 0. So if I were to plug it in, I would get negative b over 2a. Well, that's a 0 over 2. If you remember, a 0 over a number is okay. So the answer is 0. We're now going to plug it in so that we get 0 squared minus 16 is equal to negative 16. So we have a vertex at 0, negative 16. Well, I'm going to double check. Lead coefficient is positive, so I'm still going to plug him in so that I get x squared minus 16 and take a look. Of course, he crosses at 2 x-intercepts. And F, very similar problem. I have x squared plus 9. Again, a is a 1, b is 0. If I have to do this, otherwise I should understand that if there is no b there, he is 0. And all I have to do is plug that 0 in. Well, 0 squared plus 9 is 9. My vertex is at 0, 9. And he's going up. So just to verify, I go x squared. I can go over plus 9. Hit graph. Oh, well, he's positive. He starts at a positive and he goes up. So I know he has no real x-intercepts, but he has no x-intercepts. Okay. Now, we're going to talk about what our polynomials look like. As of right now, we have dealt with x squareds and x cubes, and of course straight lines. Now we're going to talk about polynomials with higher values and what they look like, so that we can take an equation and know exactly what that graph is going to look like without having to plot any points at all. So, what are the graphs of a polynomial function like? Well, they are smooth, continuous, very important, they are smooth, continuous curves. So for 14, we look at A, B, C, and D. We have different types of graphs that we've seen. And it says, which of the following functions are polynomial functions? Well, look at the very first one. Is it smooth? Is it continuous? And does it have curves? Why, yes, it does. He is a polynomial function. Look at B. Is he smooth? Kind of. Is he continuous? No, I have two different graphs there, so he is not a polynomial function. All right, A. Well, he's continuous, but he's definitely not smooth, so he is also not a polynomial function, and he has no curves. Looking at D. Well, he's smooth, he's continuous, and he has curves, so yes, he is a polynomial function. So we have a pretty good idea of what our polynomial functions are going to look like. So now we're going to talk about different aspects or parts of our polynomials that help us determine what they look like. So 15, we're going to state the degree of each polynomial function, and we're going to tell if its a lead coefficient is positive or negative. Well, the degree. Do I have a degree? Well, no, I don't, but technically I do. Right, that 3x there, he is our degree. That is technically an understood 1. That is the degree with that x. And the lead coefficient, or the LC, as it is simplified down to, is a lead coefficient of a positive 3. All right, B. Again, my highest degree in this case is a degree of 2. And my lead coefficient is that negative 4 that's right beside it. C. My highest degree. I have to pay attention to all of my values, but it's this x to the 4th here. So we have a degree of 4. Again, I'm not asking you to put x to the power of 4. I just want the 4. The lead coefficient that is with that, well, it's that positive 1/2. Oh, I'm sorry. I'm just telling you the numbers, but it's actually the sign that you want. This is a positive. This is a negative. That 1/2 is a positive. All right, D. Well, I've only got one term. The degree is a power of 5. That LC, that lead coefficient sign, is obviously just a negative. Oh, E. Well, they complicated it, but we know how to do this. All I care about is the degree and the lead coefficient. So I'm actually just going to take these two numbers in the front and I'm going to multiply them together so that I get what is an x squared. So that gives me a degree of 2. That lead coefficient is the number in front. Technically it's an understood 1, and it is positive. Now, where am I going with this? Well, that degree and that lead coefficient, they tell us things about our graph. Okay, so now we're going to decide which type of end behavior the functions from example 2 that we just did have. All right, 3x minus 9. Well, if I know anything about my graph, it's 3x minus 9, so it's going to start here at the negative and it's going up. Whoop. Well, what are my end behaviors of my graph doing? Well, they're going in opposite directions. The left side is going down, the right side is going up. So the end behaviors, we have the left side down, right side up. All right, negative 4x squared. That negative 4 is telling me that from left to right it's going down. That x squared is telling me that it's a parabola. So if I were to draw a quick graph, I don't really care. It starts up at the 1 and it's going down on both sides. So I know that the end behaviors, the left side's going down. The right side is also going down. All right, C. I have a lead coefficient that's positive, which is telling me from left to right it's going positive, and a power to the 4, which tells me my endpoints are also going up. So I know my both endpoints are going up and up. And if I know my graphs, it's going something like that. All right, we have D. We have a negative, and we have an x to the power of 5. X to the power of 5 means that it's going from left to right. It's going down, and it's going to, whoops, sorry. It's going to look a little something like, whoop, probably a little more curves than it needs to be, but from left to right it's going down, so the left side is technically going to the top. The left side is going to the bottom. X minus 1, x minus 2, we already did that lead coefficient multiplication, so we get x squared. It's a parabola. We know all about parabolas. The lead coefficient means that it's going up. So it's going up on the left and up on the right. If all else fails, then you need to take your calculator, right? We can take that negative, right? We're going to go into, turn it on, sorry. We're going to go into y equals, and we're going to put in that negative x, and we're going to say to the power of 5. That little caret key that we have is the raising it to the power of 5. We call it a caret key. And we're going to take a look at the graph. And what happens is from the left to the right, we know that it's going down. So the left side points up and the right side points down. So all else fails, graph it, take a look at it, and tell me what direction the left side and the right side are going. Now, the maximum number of x-intercepts a polynomial function can have is the same as its degree. So if it has a degree of 1, well, it can only have one x-intercept. A degree of 2, it can only have 2. A degree of 5, it can only have 5. A degree of 12, it can only have 12. The maximum number of turning points, meaning how many curves is it going to have in our graph, the maximum number of turning points a polynomial function can have is 1 less than its degree. Now, you may not have noticed, but you technically have been dealing with a function that is x squared. If we notice our x squared, there's only one curve in our x squared. We've done cubes, x cubed, right? And we have said, oh, okay, well, it's got an x cubed only has two curves, one here and one here. So you have technically been dealing with these, you just haven't made the association yet. So the maximum number of turning points is one less than its degree. So for 17, it says tell the maximum number of x-intercepts and the maximum number of turning points. So we have 3x minus 9. Remember, that is an understood 1. So it is a polynomial of odd degree, right? Power to the 1, that's an odd degree. So it's going to have up to 1 x-intercept. And of course, because we know that it's 1 less, that's 1 minus 1, there are 0 turning points, which of course makes sense because it's a straight line. So it has no turning points. All right, B. It's a polynomial of, well, let's look at our degree. This is the part that we care about right here. All right, 2 is the degree, and it's an even degree. So it's going to have up to 2 x-intercepts, and up to, of course, 2 minus 1 is 1 turning point. I hope you're catching on to some of this. Again, all we care about is the lead coefficient part. We have a polynomial that x to the power of 4 makes it an even degree because 4 is an even number. So it will have up to 4 x-intercepts, and it will have up to 3 turning points because 4 minus 1 is 3. For D, we have negative x to the power of 5. Again, I know that 5 is an odd degree. So it will have up to 5 x-intercepts, and it will have up to 4 turning points. All right, our final one was x minus 1. We know that whenever we multiplied them together, we got x squared. Notice I didn't make you multiply anything else out because I'm not looking for anything else. So the polynomial has a even degree, and it may have up to 2 x-intercepts, and of course the turning points, it will only have 1 because it's just a little parabola. So I want to recap a couple of little things, okay? And we're going to talk even and odd degrees. First of all, what do I mean? Even. So we're going to have an even degree, and it's going to be positive lead coefficient. So even degree and a positive lead coefficient means that it's going to be pointing up. Okay, and usually it'll look like this guy. Sometimes your graph will look like this guy, but either way, it's an even degree so that both ends are facing up because it is positive. If I were to have a negative lead coefficient, and it is also still an even degree, okay, it would look very similar. I have my graph, and technically because it's negative, both endpoints are pointing down. So again, whenever I go to write these, this guy is going up for the end behavior, this guy is going down for the end behavior. All right, so again, if I were to have an odd degree with a positive lead coefficient, okay, my graph is going to be going from left to right in an upward direction, right? So it's going to have some curves, but it's still, ooh, that wants to get a little funny at the end, sorry. But from left to right, it's going upwards. So I know that my endpoints are going left goes down, right goes up. All right, so now we're going to do odd degree, but negative lead coefficient. So I have my graph, and again, from left to right, it's going down so that my endpoints are up on the left, down on the right. I hope this is kind of a little bit of a representation of what you're going to see in the future and what I mean by positive, negative, even, and odd, and obviously your lead coefficients. And if you have any questions, please email me, please contact me. I will happily go through these things with you again, and in more detail if you need me to, and give you further examples. All of your, let's see, your assignment 11 is due Friday night, and assignment 12 is due Monday night. Have a good week.